This module references Chapter 12 in your textbook. The objectives for this chapter are as follows. We're going to look at solving for linear values of displacement, velocity, and acceleration in relative terms. We're going to define and locate an instantaneous center of an object, and we're going to calculate linear and angular velocities of various mechanisms by applying the theory of instantaneous centers. Remember, the key here is that plane motion is a combination of translation and rotation. What we're doing is we're combining the last two chapters, where we had chapter 10 from the textbook being rectilinear motion and chapter 11 being angular motion. Now we're going to combine these two and they will form the basis for plane motion. So first, a couple of important terms for this chapter. First, we have absolute velocity. So this is a velocity measured with respect to Earth. And this is generally the velocity that we've been looking at to date. For example, if we're discussing a velocity, the velocity of a car traveling in a certain direction with a certain magnitude, that is an absolute velocity because that is measured with respect to Earth. However, it's important to understand relative velocity. That is a velocity measured with respect to another reference object that is also moving. So perhaps you have two vehicles leaving the same spot heading in different directions, and you want to know what the relative velocity is from one object to another. This becomes really important when we're talking about linkages, because linkages move in a planar motion. They have both rectilinear and angular motion. But when you have multiple linkages in a mechanism, then you have all these bodies moving relative to each other. We're going to start by taking a look at example 12.1 in your textbook. In this example, the equation can be written as follows. So example 12.1 states the following. Starting from the same point, a car A travels north at 40 kilometers per hour, and car B travels east at 60 kilometers an hour. Determine the velocity of B with respect to A. So what we've done here is we've started by drawing out just a quick sketch of what's happening. And what we want to do is determine the velocity of B with respect to A. So as I showed in the previous slide, this is how we draw out this equation, where VB is equal to VA plus VB with respect to A. For velocity B, we know it is heading to the right or to the east at 60 kilometers per hour. So I show that below. I know that car A is heading 40 kilometers per hour north. So I show that below. And last but not least, I have the velocity of B with respect to A. I don't have an absolute value for it. I also don't have an angle, but I have an idea of what angle it is going at, right? And you might say, well, how do you know that? Well, that's because we're going to do the addition, based on that equation, the addition of vectors. This is similar to what you may have seen in previous chapters when we're adding vectors together. We're only missing the hypotenuse of this right angle triangle. And so what we can do is we can use the Pythagorean theorem, which is what we do in that next step, right? We are saying that VB with respect to A is equal to 60 kilometers per hour squared plus 40 kilometers per hour squared. And we take the square root of it. That gives us a value of 72 kilometers per hour. Now you see that I have 56.3 degrees. Well, how did I get that? Well, that's what we're doing in this third and final step here below. We are going to use trigonometry to solve for theta. Okay, so I said before that relative motion is really a combination of translation and rotation. So I want to show you two examples here. So this is an example of a linkage that's moving. We see that it is constrained in the top left corner, up at the top. We're going to call that position 1, and it is constrained to only move up and down, whereas position 2, or A there, is constrained to only move left and right. Another example that you might see, whether it's in the textbook or elsewhere, would be a, say, broom or something leaning up against the wall, and it starts sliding down. Same idea. It's still constrained, where you have the top sliding down the wall, the bottom sliding along the ground. Same idea here. And so this planar motion can be looked at from two different perspectives. The first one, if we're trying to say solve for what the velocity at b is, we can state how we did it before. VB is equal to VA plus VB with respect to A. Now, where you might be confused here is especially with this subscript and which one comes first. A really easy way to look at this is that I want to solve for VB. So I'm going to set that equal to the other velocity that we're looking at, which is VA. And I need to add it to some sort of relative velocity. How do I know if my subscripts are correct? Well, a way to look at this is to take those subscripts. So if I were to say go A over B, what I'm saying is try multiplying them together. So A times A over B, and you get A squared B, which doesn't work. What you want is to have these subscripts work out, like for them to cancel out. So if I instead did B with respect to A, then I can see that A and A cancel out. And what we would be left with is VB equals VB, which would be true. Okay, so that's just how you confirm whether or not your subscripts are correct. Okay, so again, we're solving for, in the top line here, we're solving for the velocity at B. So we're going to set that to the other velocity that we know, VA, and then we're going to add the relative velocity of B with respect to A. So when you're looking at these problems, imagine it like this. I want to know what the velocity of B is with respect to A. That with respect means put yourself in the shoes at A. Meaning, imagine yourself fixed at point A. Okay, you're standing on point A. This is a rod that is, the size of, a large room, and you're standing at point A, and you want to know what is happening at B. Well, if you're standing at A, even though you're moving to the right, B is not going to look like it's going down. It's actually going to look like it's moving across from you. It would be like you are fixed at point A, like you're not moving, because you're looking at point B. You're not looking at it relative to Earth. You're looking at point B. So it's like you're not moving, but VB is rotating around you if you were standing at point A. Okay, so this is always going to be the case. When you say VB with respect to A, it means position yourself at that with respect to. So position myself at point A, and VB rotates around me. That means that we have an angular, as we see here, an angular velocity we're rotating about, and that the actual direction of B with respect to A is 90 degrees to that rotation arm. So again, this will help us create our velocity triangle. In this case, it's pretty easy because we know that VB is going down no matter what. It's constrained. VA is going to the right no matter what. We're not adding them together. They have to equal each other. So they're going to go away from each other. And we look at our equation. We said that right here, VB is equal to VA plus V. Well, let me fix that. Remember, I was just showing you the example. This should be VB with respect to A. And so that VB with respect to A has to go from the tip of VA and has to then touch VB. And so we know it's coming down. And that actually would align with what's shown in the diagram to the left. That VB with respect to A is at about 90. It is exactly 90 degrees to that rod. And so that would be collinear with that triangle that we see there. So that works. From there, we can then solve for any one of those velocities or angles. So that's looking at it from the perspective of B. We want to solve for VB. What if we want to solve for VA? VA is equal to VB. VB just goes down. And then we're going to add VA with respect to B. So in this case, it's like positioning yourself at position B, and A is moving with respect to that. So again, your station at point B, everything is rotating around you from that point. Once again, we can create our velocity triangle, and notice how the velocity triangle looks exactly the same. What is the difference? The only difference is that now instead of having VB with respect to A, we have VA with respect to B, and they are just 180 degrees to each other. It's like one is positive, one is negative, kind of opposite direction is all. So we'll get to some examples in a minute. One of the things I wanted to discuss was that this can be done with acceleration as well. Relative acceleration can be handled using the same type of equation. However, each acceleration term consists of both tangential and normal acceleration components. So as a result, we're actually dealing with 6 acceleration values and not just 3. Okay, so let's take a look at example 12.4. Now this example can be found on page 394 of your textbook. In this problem, it asks to determine the linear velocity of end A of the bar shown if the velocity of B is 16 inches per second to the right. And we also want to determine the angular velocity of AB. So let's start by drawing out the figure. As it said in the problem statement, it said to determine linear velocity A and angular velocity AB. I've drawn all the knowns. We know that the wall is angled at 60 degrees relative to the horizontal. We know that VB is 16 inches per second to the right. We don't know the velocity at A, but we do know it has to be traveling along that wall. So I've just drawn the velocity in that direction. We also want to determine the angular velocity of AB. So that just means the entire linkage. What is its angular velocity? That's another thing we're going to need to figure out. So the very first step that we always complete when we are doing these problems is to write out our relative velocity equation. So for part A, we are going to say that VA is equal to VB plus, remember our subscripts need to cancel out here, so it would be VA with respect to B. Now what I'd like you to do is provide everything that's known here. We do know that VB is going to the right, and we do know it is 16 inches per second. We know that VA is going down in this direction at 60 degrees. And in case you aren't too sure about that, we do know that the bottom left, it shows on the wall is 60 degrees. But if we use the Z law here, I'm just going to extend out a horizontal from point A, then we know that the angle between that horizontal and velocity of A is also 60 degrees. So that works. The only thing is we don't know what direction or magnitude the velocity of A with respect to B is. And so there's a couple of things that we can do. Why I always ask you to provide all the knowns here is because the very next step that I always ask is that you create the velocity triangle. So we have two velocities. We should be able to get an idea here of what this velocity triangle looks like. We do know that we have 16 inches per second, and it's going in the horizontal direction. We do know that velocity A, we don't know its magnitude, but we know it's going down that direction because it is at a value of an angle of 60 degrees here. So this would be, for us, this would be VA. Now we know that VA with respect to B must be in between, and since we're adding it to VB, it must go down in that direction. So this would be VA with respect to B. We just don't have any other information yet, so we're going to need to try to solve for that. Now the problem is that we only have one angle and we only have one side. If we did know what VA is, we could have used the cosine law, but we don't have that. So there must be a way that we can get at least one more angle out of this. And that would be going back to how we interpret what VA with respect to B is. So what I'm going to do is I'm going to just draw out that linkage again. Okay, and remember VA with respect to B is like you're positioning yourself at B, and VA is then rotating about that point. So that means that if we know that, okay, so this is A here, this is B here. So we're going to pretend like we are positioned at VB. And so that means it's kind of like this, where it's constrained to just rotate here, that it's rotating in this direction here. That means that the velocity of A with respect to B has to be in this direction because it has to be 90 degrees here. So this would be your VA with respect to B. Okay, it kind of lines up with what our velocity triangle looks like, but is there any information that we can get from here that would help us? Well, one of the other pieces of information that I did forget to write in here that is given is that there's 40 degrees in this corner. So that would mean that this is at an angle of 40 degrees. Still not all that helpful yet. So what we're going to do is I'm going to draw out a line across here just to show that this is a horizontal. If this is 40 degrees, we have 40 degrees at the bottom. Again, using the Z law, we have 40. I'll just go back to using my green here. So I'll have 40 degrees in that angle. Now we can see that we have 40 degrees plus 90 degrees. That entire angle on that horizontal line has to be 180, right? So if we have 90 and 40, that would be 130. And so this value in here, if you want to call that theta, theta would have to be equal to 180 minus 90 minus 40 degrees, which is equal to 50 degrees. And since that's 50 degrees, we know that we have 50 degrees in our velocity triangle there. And since an entire triangle needs to be 180, that means that the angle down here is 70 degrees. So now we can go back to our equation here and fill it out. So we know that VA with respect to B is 50 degrees. Excellent. And why is that so good? Well, that means now, since we have enough angles, we don't have to use the cosine law. In fact, we can use the sine law, which is even better, just because it's easier, right? So we're going to take VA and we're going to use the sine law. So that's sine 50. Remember, it's the opposite angle is equal to the one that we know, which is 16 inches per second over the opposite angle, which is 70 degrees. And if you want to continue that, we also have the other side, which is VA over B, or VA with respect to B over sine 60 degrees. So now from there, what we can do is we take this first part here, we can solve for VA. So VA is equal to 13 inches per second, and we know that it is going at an angle of 60 degrees. And that is one of the parts that we need to solve for. So VA is equal to 13 inches per second at 60 degrees. Next, it says it wants to know what the angular velocity is of the entire assembly. So of the linkage, what's the angular velocity? We can see that if we are positioning ourselves at point B, it looks like VA is rotating about point B. So it does have a rotation. That would be the equivalent of the entire linkage that's rotating. It's rotating and translating, but it does have a certain angular velocity. So that angular velocity can be determined if we know what the linear velocity of A with respect to B is. And you might say, well, gee, how is that possible? Well, remember, we can, going back to previous units, we can convert between angular velocity and linear velocity. remember that V is equal to R omega, right? So if we use our subscripts here, we can then say that V A with respect to B is equal to RAB times omega AB. So we just need to solve for the velocity of A with respect to B. And we can do that with this equation, the other half of that sine equation, of the sine law equation. So VA with respect to B is equal to 14.7 inches per second. And we know that it is going at an angle of 50 degrees. So we can then sub that into this equation here. We just need to solve for omega AB. So omega AB is equal to 14.7 inches per second over its length. And the length is given. If we go up, we can see that it is 12 inches. So that's 14.7 inches per second divided by 12 inches gives us 1.23 rads per second, and it is rotating counterclockwise. So that's equal to omega AB, and that would be the second half of our solution for this problem. Okay, some important notes when completing these problems. First, a correct relative velocity equation will have subscripts that cancel out. So remember that on the right-hand side of the equation, if you were to multiply the subscripts together, they would cancel out such that the left-hand side equals the right-hand side. A relative velocity such as VA over B is the velocity of A with respect to B. What that means brings us to our third point, which is that a velocity for VA with respect to B is the velocity that A appears to have when viewed by someone stationed at B. The velocity of A with respect to B is equal and opposite to the velocity of B with respect to A. Also, you need to show all possible information of vector magnitude and direction under each term of the equation, then draw the vector triangle. When you're solving these problems, whether it's for an assignment or a test, I will be marking A points for each of those. First the equation, then writing everything that's given, then the triangle. So those are three pretty easy marks. After that, trying to figure out the rest of the information might be a little bit more difficult. So as long as you do those first three things, that at least sets you up for success on a problem like this. So let's take a look at example problem 12.7, and this is on page 398 of your textbook. In this problem, it states that the velocity of point A is 10 meters per second to the right for the system shown. Using the relative velocity method, determine the angular velocity of AC and the linear velocity of point C. So let's draw out this problem once again. We have a linkage with a velocity at A going to the right, and it's in a track, so it can only go left and right. We also have point B, which is in a track, and it can go only up and down at that angle of 50 degrees. And then we have point C. And what we'd like to determine is what is the angular velocity of AC, that complete linkage. We also want to determine what the velocity at C is. Okay, so it's not in the track, so it will move separately from B. So that's the very first thing I just want to point out, is that some people kind of get messed up here because they think, well, as long as I find out what B is, that equals C. And it doesn't, right? Because those are two different points on a part that is not moving just linearly and not just rotating. They are both moving linearly and are rotating. So that's a key difference here. So what I always suggest is you start from the end that's known and work your way to the other end of the information. So we're not going to jump from A to C. We're going to go from A to B And then from there, hopefully we can figure out what's at c. So that means that very first step in this problem is writing out our equation. We have VA, so let's solve for VB. So VB is equal to VA plus the velocity of B with respect to A. Just make sure our subscripts work out, and they do. Next step is to provide all the knowns below that equation. So A is going to the right, and it's going at 10 meters per second. If A is going to the right, we'll assume that it probably means that VB, it has to go at 50 degrees, but is it going up or down? I'm going to assume that it is going up. If you get the wrong direction, it's not the end of the world, because you'll just end up with a value that is negative. So we have 50 degrees here. Next, we need to know what the velocity of B is with respect to A. Okay, and we're not 100% sure again how to finish that off. So you can either start by drawing out your velocity triangle, or what do we do to figure out the direction of B? Well, we can just redraw that linkage. So I'm going to draw the linkage real quick. I'm going to bring up this linkage here where we know that point A, of course, is the bottom, point B is here. And since we are stationed at point A, remember it's B with respect to A, B appears to actually be rotating. So it would look like it's probably rotating something like that. And so that means that the velocity of B is 90 degrees to that rotation arm. So let's see if that helps us to create our velocity triangle. I'm going to start with what's known. So we have VA going here at 10 meters per second. I also know that VB is going at 50 degrees with respect to horizontal, and it's got to be going away from VA, since that's what we have in the equation there. So this is VB. And based on that figure that we drew up in the top right corner, we know that we don't want to go too far with VB, otherwise that won't look quite right, will it? It needs to align with that. So this is what we're going to do. We're going to say that it's 10 meters per second, and you might say, well, wait a second, which one again is it? Is the arrow up or down here? Well, it's got to be going up. Not just because that's what's shown in the top right corner, but because that's what we would have to do when we're adding vectors like this. So this is VB with respect to A. Now remember that this is 50 degrees. Is there anything else that we can get from the figure to help us finish out this velocity triangle? Because it's just like the last problem. We have 10 meters per second and we have 50 degrees. Those we know for sure. Those two we know for sure. But we don't have anything else. And so again, that's not enough to solve for our angles or our sides, the sides of the triangle. And so this is where I would say it's helpful you can redraw this as many times as you like. Okay, whatever it takes to help you out here. I'm just once again going to redraw the link. Okay, and I'm going to show all my points here. So I've got A, show that here. I've got B. Okay, I do know I have C up top. I know that I have this velocity, and that's at 70 degrees. Let's draw out a horizontal line from point B. See what else we know. Okay, we do know that velocity at B has to be, this full angle is 90 degrees here. If we know that the angle between velocity B and the link is 90 degrees, we drew in this horizontal line, and now you can start to see, oh, we've got a z-law in there. So the z-law would state that the angle here is 70 degrees. And if that full angle is 90 degrees, that means that the small angle in here has to be 20 degrees. Okay, so while that might not have been possible to see in our original figure here, maybe not even here. This is why I always highly suggest you draw it out a few different times for each of the things that we need to solve for. So first, drawing this linkage where it's fixed at point A to figure out the direction of B, and then I draw it again with the angles that I do know from the figure. So I know that velocity B has to be traveling at 20 degrees with respect to the horizontal. That means we have 20 degrees in this corner. Okay, and that means we're left with theta, but theta must equal 180 minus 50 minus 20. So that means that theta is 110 degrees. So we even have our theta in there. We have all of our angles. Excellent. That means now, once again, we can use the sine law to solve. We can say that VB with respect to A, and I see I made a mistake in here, so I'll just get rid of that in my velocity triangle. It should be VB with respect to A, over the opposite angle, which is sine 50, is equal to 10 meters per second over its opposite angle, which is sine 110, which is equal to VB over its opposite angle, which is sine 20 degrees. Okay, so now we can solve for, well, if we start with VB, we can say VB, or VB with respect to A, I should say, that's equal to 8.15 meters per second. We know that that's going up at an angle of 20 degrees. Now, why does that help us? Well, remember that if we have the velocity of B with respect to A, that means we should be able to figure out the angular velocity. Okay, so that's what I'm going to use that for. Remember that VB with respect to A is equal to RAB times omega AB. Therefore, if I rearrange for omega AB, I would have 8.15 meters per second over its length, and that you can get from the figure is equal to 0.4. So that total angular velocity is 20.4 rads per second counterclockwise. Now you might say, well, okay, Shane, but it said what's the angular velocity of AC? Well, just like a disk before in our angular motion, any point on a body that is spinning has the same angular velocity, right? It is independent of its radius, and so therefore omega AC is equal to omega AB equal to 20.4 rads per second counterclockwise. Okay, so that is the answer for part A of the problem. Okay, remember, next we need to solve for the velocity at C. So that's why I didn't right away here solve for VB, because it wasn't really necessarily required. We need to then solve for the velocity at point C. Now, the only way to do that is to basically redo what we did. We are going to start by writing out the equation. VC now is equal to, now you can go from VA or you can go from VB. It doesn't matter which relative point, but we'll start with what's given. So that's VA plus VC with respect to A. Okay, so similarly to the last problem, if we were to draw out our figure here, okay, we know that the velocity of A is going to the right. And if we want to determine what the velocity of C with respect to A is, we know it has to be just like B. It's going to be 90 degrees, so this is your velocity of C with respect to A. Now the question is, what is the direction of the velocity at C? This is where it gets definitely a little bit confusing. I'm going to go and continue what I always say is you write the equation, then you write out what's known. So I'm going to say that as we had before, where is it? Oh yeah, right there. So VA is equal to, so that's 10 meters per second to the right. Okay, we know that the velocity of C with respect to A is at an angle and that would be also 20 degrees, kind of like VB with respect to A. We have that, but we don't have a magnitude for that. Isn't a huge deal yet, because we could start drawing out our velocity triangle where we go like this, 10 meters per second, and then we go this direction, the velocity of c with respect to a. Here's the thing though, is that we don't know how far we go with that magnitude. If it's a short magnitude, then the velocity of c would look, something like this. The way I've drawn it right now, it would look something like this. We don't really know. So it would be helpful if we knew what the magnitude of velocity of c with respect to a is. And here is why solving the first part actually helps us with this. Because remember what I said about this last part that we did in part A, where we solve for the velocity of, using the velocity of b with respect to a, we solve for the angular velocity, and that angular velocity is the same no matter where you are on that body. Right, so let's use that to our advantage. We can then state that the velocity of c with respect to a is equal to RAC times omega AC, where omega AC is equal to omega AB, which, remember, we had already found over here of 20.4 rads per second. So as long as we know what the radius arm is from A to C, which we do, then we can solve for the velocity of C with respect to A, which is just going to be equal to a total of 0.6, because it's 0.4 meters plus 0.2 meters, times 20.4 rads per second. And so we get a magnitude here of 12.2 meters per second at an angle of 20 degrees. So we're going to add that to our equation up here. We know that it is 12.2 meters per second. And that will then help us solve our velocity triangle. So I'm just going to redraw that over here, where I know that we have 10 meters per second. That also then tells us that 12.2 is going to probably bring us out, since this is only 20 degrees, a little bit past the start there. So we're going to then draw this. This is 12.2 meters per second. And so our last but not least is our velocity at point C, where, yes, we have 20 degrees in here. That means that VC is actually going up in this direction. So you can see it's maybe not what you would have expected. Remember I said that the velocity at point C was not equal to B. It certainly is not equal to B here. So we need to solve for this. Now, the great thing is that in this particular case, we have two lengths and we have the opposite angle to the length that we need to solve for. So this is a perfect example where we can use our cosine law, where VC squared is equal to 12.2 squared plus 10 squared minus 2 times those two lengths, 12.2 times 10 times the cosine of the angle, which is 20 degrees. And what we're going to get here is VC is equal to 4.42 meters per second. Now, we need to figure out what that angle is. So that's the very last step, because we do have our magnitude. It is a vector, so we need our direction as well. So if we just go back to this, we need to figure out, what this angle here is, which we can call beta. Now that we have three sides and we have at least one angle, we can now use the sine law to solve for any of the angles, including that beta angle, which would be here. So all we would have to do then, as I said, is use the sine law. So we can say that we are going to do 12.2 meters per second over the opposite, which is sine beta, the one we want to solve for. We just found 4.42 meters per second, and the opposite angle there is sine 20 degrees. So if we rearrange, we can solve for beta, and you will end up with an angle of 109.3 degrees. So therefore, the velocity at c is equal to 4.42 meters per second at an angle relative to the horizontal of 109.3 degrees.